So, the energy of the photons should not be confused with brightness or intensity of the source. For example, the people have a feeling that the energy, higher the energy, more is the brightness. That is wrong notion. The energy has nothing to do with the brightness or intensity of the source, but it does relate to the color of the light. Yes, to some extent it does relate to the color of the light. The power of a light source is given by P is equal to number of photons and photon energy. So, if the number of photons are more, if the photon energy is more, then the power of intensity of the light source will be high. So, it is the energy of a beam of radiation that reaches a given area per second, not the given point. So, intensity of a radiation, what it is the power emanating per unit solid angle, how much of the energy is coming out in a particular solid angle. Just like when you point a torch, if you point it very near the earth, it will be a small spot, but if you raise it and then open it into space, it will describe a bigger arc. So, that is what we mean here. Intensity of a source of ray is the power emanating from the unit solid angle. That is how we can define it. Now we come to, having understood the properties of electromagnetic radiation, we will consider how the transmission of radiation occurs. Okay. So, the rate of propagation of electromagnetic radiation through a transparent medium such as atoms, ions, molecules, particles, etc., should be less than that of vacuum. This is understood sort of in a rough way, because if there is vacuum, there is nothing to stop the a corpuscle, a photon passing through a vacuum and then reaching the other end. But if there are atoms and molecules and other things, gases in between the space, then it will be interacting with them and proceeding at a lower pace. So, the normal expectation is the rate of propagation of electromagnetic radiation through a transparent medium is less than that of the vacuum. But if it is not a transparent medium, question does not arise, because it will look opaque. However, frequency change will not be observed, which means that the permanent energy transfer to the medium does not occur. See, if earlier we have said frequency corresponds to, any frequency corresponds to fixed amount of energy. So, if a radiation passes from one end to the other end without and still having the same frequency, it means the medium has not interacted with the photon. The permanent energy transfer to the medium does not occur at all. Therefore, the interaction involved must be only temporary. So, how do we define that? It can be due to temporary deformation of the electronic cloud associated with atoms and molecules. So, this interaction occurs between 10 raised to minus 14 to 10 raised to minus 15 seconds. Within that span of time, if you know what is a second, right, 10 raised to minus 14 seconds, the whole interaction occurs and it is completely over. So, the velocity of the radiation in the media is the wavelength dependent on the refractive index of the media. If the refractive index of the media is 1, there is apparently no change in the velocity. The variation of the refractive index with respect to wavelength, that is known as dispersion. what are we saying now? The variation of the refractive index of the medium with wavelength of the incoming radiation. If there is a variation, then we say that the electromagnetic radiation is dispersed. So, this is how transmission of radiation occurs. Now, you can imagine that dispersion is not a simple phenomenon at all. Dispersion curves usually show two regions. One is normal dispersion, that results in the gradual increase in the refractive index with increasing frequency, and anomalous dispersion occurs at frequencies at which sharp changes occur, coinciding with natural harmonic frequency of some part of a molecule or atom or an ion, leading to an absorption of the photon or absorption of the radiation or absorption of the beam. In spectroscopy, dispersion curves are important for optical components such as lenses. Why? Lenses should show minimum dispersion but uniform dispersion. Most suitable components for the manufacture of lenses are those in which refractive index should be high and constant. If the refractive index is high, that means a thinner material would suffice for the job. If the refractive index is low, I need a thicker this thing. You can imagine when an older person will require a thick glass. A younger person, if at all, if he needs a glass specs, he requires a very thin number, because thin glass, because the number would be small. So, similarly, if the dispersion is uniform and dispersion is very high, then the components of a spectroscopic instrument would become thinner. That is the beauty. So, we look for materials which are having high refractive index. So, most suitable components for the manufacture of the lenses whose refractive index is high, and it should be constant also. This results in reduced chromatic aberrations. What is a chromatic aberration? Near the edge of the lens or something like that, there will be the image transmission will not be proper. So, it may be either elongated or shortened or something like that. You would have seen in a number of day to day examples where you go and look at any curved mirror, near the edge the image is always distorted. Okay. So, for the regular spectroscopic components, we need materials which are having high refractive index, because the image of the substance should not be disturbed. Now, the fabrication of prisms, therefore, refractive index should be large, but also highly frequency dependent. So, prisms, lenses, mirrors, these are all parts of our spectroscopic instruments. So, that is why I am teaching you all about the optical components now with the interaction between electromagnetic radiation. So, initially we have described what is known as electromagnetic radiation, how we characterize it. Now, we are coming to properties of the electromagnetic components interaction with different materials. Now, we are talking about air, and that is transmission through the refractive index. Air has got refractive index. Similarly, if I allow radiation to pass through water, then water is also having refractive index. Like that, we are talking about this thing. So, if I want to transfer electromagnetic radiation through a prism, then I can choose the particular frequency, because the refractive index of a prism is a function of the material. So, now we talk about reflection. So, reflection of a radiation, what it means, we are familiar with the whole phenomena. Mirrors reflect the radiation falling on them. Without any loss of the incident radiation power, so that means if you stand in front of a mirror, you will see the reflection, and reflection should be as true as possible, otherwise you yourself will feel, am I really like this? So, without any loss of the incident power, if the mirror works, then you will get a very high quality image. Hence, they are used as optical components of a spectrum, of a spectrometer. Concave mirrors reflect the radiation as well as concentrate the reflected radiation at its focal point. If you pass the radiation through a concave mirror, all the radiations will focus on a particular point, and at that point the image will be perfect and short and sharp, etc. So, when radiation crosses an interface between the media, resulting in a refractive index of some amount of reflection always occurs. So, for a beam entering an interface at right angles, if I have a beam like this, a radiation entering at right angle straight away perpendicularly, the reflection, the right angles, the fraction reflected is given by IR by I0 is equal to N2 minus N1 whole square divided by N2 plus N1 whole square. This is all high school physics. I am not teaching you anything brand new, but all this you would have studied in your high school, but I am just refreshing your knowledge with respect to reflection, refraction, radiation, etc., because it is later on when we study the instrumentation, I do not want to go into detail regarding the optical component. I will simply say that it is reflected, that it has got so many reflectors, like that I can proceed. So, in this expression IR by I0 is equal to N2 minus N1 whole square divided by N2 plus N1 whole square. The I0 is the intensity of the incident beam, IR is the reflected intensity, and N1 and N2 are the refractive indices. Okay. So, this is how a refraction phenomena occurs. You can see this is a glass, and then this is perpendicular to the glass. If I allow the light ray to pass through this, it will not proceed in the same direction, but it changes direction depending upon the refractive index of the glass. And then when it gets out of the glass, again the reflective index will change and it will be joining the same direction, but not the same point in the space. So, when radiation passes at an angle through the interface between the two media having differing densities, an abrupt change in the direction occurs. This is called refraction, but owing to the changes in the velocity of the radiation in the two media, the extent of refraction is given by Snell's law. What does it say? Sin theta 1 bar sin theta 2 is equal to N2 by N1, that should be equal to velocity of the radiation in medium 2 and to the ratio of velocity in the medium 1. So, in vacuum we generally consider it as having 0 the velocity, so and N1 is unity. So, N2 vacuum is given by sin theta 1 vacuum divided by sin theta 2. So, refractive index of various materials are measured with air as reference, not vacuum, which are available in databases. If you look at Google, if you hit Google and find our refractive index, you hit Google refractive index of material, you will see so many refractive index of water and then air, liquid, vacuum, acetone, benzene, like that, and all such data are useful at some particular point of time during the construction of the electromagnetic radiation. So, similarly we can talk of scattering of radiation. So, what is scattering? Scattering is momentary absorption of radiant energy by atoms ions or molecules, followed by re-emission of the radiation in all directions. That means, if I have a particle here, radiation comes and hits, and then the radiation will be dispersing in all directions, that is scattering. Now, you would have seen a number of examples like this, that if you put a glass of glass ball in front of on a table and allow radiation to come and hit, all the area around it is illuminated. Such things you would have seen number of times in all your day to day life, and even water can act as a point of scattering. Now, the point is, particles having comparable dimensions to that of incident radiation removes most of their radiation by destructive interference. What happens is, the radiations are moving everywhere. Some of them will interact constructively, increasing the light. Some of them will destroy each other, because the frequencies are not matching. So, this is again a high school physics experiments you would have done, but what is important is a very small amount of fraction of the radiation is transmitted at all angles from the original path, and its intensity decreases with particle size. If the particle size is smaller, intensity decreases, increases. So, scattering by molecules or aggregates having smaller dimensions than the incident radiation is called Rayleigh scattering. That means, scattering by molecules or aggregates having smaller dimension than the incident radiation. That means, incident radiation must be reacting with atoms and molecules and electrons and things like that, then it is called Rayleigh scattering. Larger molecules scatter radiations in different quantities in different directions. This is called as Mie scattering. So, there are two types of scattering, one is Rayleigh scattering, another is Mie scattering, and when the scattered radiation is quantized, like those occurring in vibrational energy level transitions in molecules as a consequence of polarization process, then it is called Raman scattering. We are not going to study any of these scattering phenomena in our atomic absorption spectrometry course, but it is a part of the optics of the instrument. That is why I am describing you some of these experiments. So, now we should also know about polarization of radiation. An ordinary beam of light consists of electromagnetic radiation. This I have already told you a number of times, and then it consists of a bundle of electromagnetic radiations in which vibrations are equally distributed among a huge number of planes centered along the path of the beam. This is the general picture of how an electromagnetic radiation moves. Now, viewed end on, that is, if you stand at the end of the at one end and see an electromagnetic radiation proceeding towards you, it looks like an infinite set of electric vectors fluctuating from 0 to maximum amplitude A. I have shown here, here you are, I assume that you are standing here on this point, you are seeing a radiation coming here this side. You can see that number of vectors are pushing towards you. Okay. If you stand this side, if you stand this side, of course, it is a different phenomena, but what I am saying is the vector in any one plane, say xy, can be resolved into two mutually perpendicular components. That we have already said that also, because we have said the particles will move from it has got two components, perpendicular and horizontal. So, removal of one of the two resolved planes, that is one either horizontal part or the vertical part, it produces a plane polarized beam. This occupies a single plane. So, radio waves emanating from an antenna and microwaves produced by klystron tube are plane polarized. If this is for your information. What is a plane? Because another part is removed. So, radio waves, how do we remove that? We put an absorber. So, it will absorb only the vertical component or the horizontal component. So, the example is radio waves coming from an antenna and microwaves produced by klystron tube are plane polarized. So, polarized ultraviolet and visible radiation is normally produced by passing the electromagnetic beam through a media that selectively absorbs, reflects or refracts that vibrates only in one plane, that is plane polarization. So, you can imagine now here this part is the incident beam, it has all components, but in space all the components are in space and they are scattered everywhere. Now, I put a polarizer and this polarizer is nothing but a small piece of mica or something like that, transparent mica. What it does? It removes all other part components of the electromagnetic radiation, but allows only one direction, single direction vertically. This is known as vertically polarized light wave. So, here I can put one more and remove what is there at the bottom also, and then I can have one more this thing. So, the now I can this part which I have explained to you just now is useful in the atomic absorption instrumentation, which we will describe as the Zeeman effect atomic absorption spectrometry. Shall we stop here or continue another 5-10 minutes? Avinash?
1 hour over, sir.
Over, huh? Shall I stop?
For 5 minutes, sir. We can continue for 5-10 minutes, sir.
5-10 minutes, okay.
Okay, sir.
Right, I will continue.
Okay, sir, you can continue.
Yeah. So, in continuing our discussion, what we are going to do now is describe an electromagnetic radiation with respect to dispersion. And dispersion, as I have told you earlier, it is a complex phenomena. Dispersions occur usually they show two regions. One is normal dispersion, in which there is a gradual increase of refractive index with increasing frequency, and there is another part that is known as anomalous dispersion that occurs coinciding with natural harmonic frequency of some part of a molecule or atom or ion, leading to the absorption of the beam. So, the dispersion can be of two types, one where there is no change and one where another part is part of the radiation is absorbed. That means, the intensity of the light coming out of after dispersion would be lower than what is there in the intensity of the light before. So, in spectroscopy especially, dispersion curves are important for optical components again, such as lenses. Most suitable components for the manufacture of lenses are those in which refractive index should be high and constant. So, there is always a search for good refractive index materials in spectroscopy. They could be glass or quartz or something like that, and the refractive index can be changed by preparing glasses with different kinds of compositions of the silica component, and then lead, that gives still clear glasses. Most suitable components are those in which refractive index should be high and constant. This results in again in reduced chromatic aberrations. For the fabrication of prisms, what we need is a refractive index should be large, but also should be highly frequency dependent. If the frequency dependency is high on the refractive index, then it is a better material for spectroscopic components. Now, I am trying to show you here what is known as normal dispersion and another is anomalous dispersion. This part is known as normal dispersion, because we know that these are the frequencies on the x axis, 10 raised to 13, 10 raised to 14 and 10 raised to 15. This is in infrared, this is in again in infrared, this is in visible, this is in ultraviolet, and here you can see the refractive index is high here and it is very uniform here, and then here in this range it is not at all uniform. So, the anomalous part is between this range area and normal dispersion is in this area, very uniform. So, the diffraction of radiation. So, this is also another important aspect of radiation. Usually diffraction refers to the bending of a parallel beam of electromagnetic radiation as it passes through a sharp barrier or a narrow opening. It is just like prism. Okay, you send the radiation through a prism, it starts bending, and it is a consequence of interference, because diffraction, which can be easily demonstrated in the laboratory. It is all these things we know in high school physics and college physics, that a lot of experiments have been done, and you also would have done if you have passed intermediate science with physics as one of the subjects. Even in high school level they try to teach you all these things, but here we are only trying to refresh ourselves. So, when a parallel beam of light is allowed to pass through a pinhole, two closely spaced pinholes are seen on a screen placed across it. This is a very standard phenomena, you can do the experiment even at home. So, if the radiation is monochromatic, that means if we use a radiation containing only one wavelength, that is monochromatic, it is one wave, single wavelength light is known as monochromatic light. So, if the radiation is monochromatic radiation, a series of dark and light images appear perpendicular to the plane of radiation. Very common example is like this. What you do is, you take a, this is not there, you take a plain paper and make a pinhole and then allow the radiation to pass through and put a paper on the other side. Okay. So, this is how this whole experiment has been done. You can see the picture now. Now, in this picture the light radiation is coming out from this end, and then there is a small hole here, and you can see a range of dark and white patches all along the radiation, but you can also see that the light is proceeding from like this. Again light is proceeding, coming from this side, it enters the pinhole and then proceeds like this, describes a bigger and bigger angle. So, the angle here is very small and the angle here is bigger, that is the range, area is bigger. So, this is the phenomenon of diffraction, and this occurs because of the constructive and destructive interferences of the light that is emanating from the same pinhole. So, in the above figure, this figure, you can see that if you draw a picture of the geometric picture, you will see that I do not know whether I have put it or not, I will try to show you in the next class what it is. The two beams are in phase at D, and it is necessary that they should correspond to the wavelength of the region, and two beams which are not in consonance, they destruct themselves and show 0 or dark patch. Now, the white patch is also seen at different wavelengths, 2 lambda, 3 lambda, etc. So, we can arrive at an expression known as n lambda is equal to B c sin theta, where n is a number called as the order of interference. So, we will continue our class in the next class, we will continue our discussion about this in the next class, and then we will proceed to determine the other components of the optics of the spectrophotometer or a spectrometer for that matter. Thank you very much.